Hello, this is Mr. Bess, and welcome to the world of limits. We will be able to evaluate limits numerically, graphically, and algebraically. First off, what is a limit? If f of x becomes arbitrarily close to a unique number L as x approaches c from either side, the limit of f of x as x approaches c is L. Now we're probably going to have to read that again. There's a lot going on there. So if the function becomes arbitrarily close, okay, so that's important. It becomes close to some unique number L as x approaches this c value from either side. So from the left and from the right side, the limit of f of x as x approaches that number c will represent the limit, or in this case is L. So once again, a lot going on there, but what we're trying to do is as x approaches some value c from the left and from the right, what is your y value getting closer and closer and closer to? And if it's approaching some value, then that represents the limit. So limits can be found numerically, graphically, or algebraically, and we're going to look at all three of them today. Alright, the first example we're going to start with is numerical. So we're going to use a table to estimate the function 3x minus 2 as the limit approaches x. On the first example here, we're going to use a table to estimate numerically the limit as x approaches 2 of 3x minus 2. So what you can see here is I've created a table, and you notice that we are from the left approaching 2, and then also from the right approaching 2. We don't care what happens at 2, that's why that question mark is there. A limit is as it approaches that number, not what that number actually is. So we're going to look at numbers from the left and from the right of x equals 2, which is what the limit is asking. As x approaches that value of 2, which is your c, what is the function getting closer and closer to? So to be able to do this, one way to do this is using your graphing calculator. When you go in your graphing calculator and you want to plug in your function, you're going to plug in your function y equals 3x minus 2, just like you always do. And then you're going to go to your table setup. Alright, and your table setup on your graphing calculator is the window button. So if you press second window, you'll see it says TBL set. Okay, and so when you get to this, what we want to do is we want to set the table up so that the table start value is at x equals 2. So we'll change that number right there to 2. Alright, and then the next one is delta table. So that's the change. How do you want your table to change? So we want to know as it gets close to 2. So we're going to make it 0.01. Okay, and so now when you go to your table, most likely, since you're starting at table or at x equals 2, it'll actually take this value and it'll be the first one on the table. So I've moved mine to center it so you can see exactly the left and the right side, kind of the symmetry of that. So at x is 1.97, the y value is 3.91. So we're going to fill out the table. So when x is 1.97, 3.91. When x is 1.98, 3.94. And when x is 1.99, we get 3.97. Now, as I said, we don't care what happens at 2, so that's going to stay the question mark. Then at 2.01, it's 4.03. At 2.02, it's 4.06. And at 2.03, it's 4.09. So what we're trying to figure out and estimate this numerically by looking at the table, and as the values get closer and closer to the x value of 2, what does the y value look like it is approaching? So you can see the 3.91, 3.94, 3.97, and then the 4.09, 4.06, and 4.3. So it looks like this is approaching 4. So therefore the limit of 3x minus 2 as x approaches 2 is equal to 4. And that's what a limit is. As x approaches that value from the left and the right, what is the y value getting closer and closer and closer to? So this function is continuous because it is linear, but for graphs that are not continuous, finding limits can be a little bit more difficult than that. So let's go ahead and take a look at the next one. So on this next one here, we're going to still use a table to estimate numerically the limit, but this is f of x equals x divided by x, the square root of x plus 1 minus 1. So you can see on the table already that at x equals 0, unlike the last one, we have an error. So we don't know what x is, or we don't know what y is when x is 0. And it doesn't matter anyways, we just want to know as it approaches 0. So as we plug this in to our calculator, you can see I started the table at x equals 0 this time because that's what the limit is approaching. So as, or not the limit, sorry, as x is approaching 0. So the table start, we're going to start at 0. And so now when you see the window where the table is, you can see my values there. So I'm going to write these down in the table. So when x is negative 0.03, that's 1.9849. At negative 0.02, it's 1.9899. And at negative 0.01, it's 1.995. And then once again at 0, that's the question we're answering in just a second. So at 0.01, it's 2.005. 0.02, 2.01, and 0.03 is at 2.0149. So once again, as you're looking at the table numerically, what does it look like is happening to your y value as x gets closer and closer and closer to that 0? It looks to be approaching the number 2. So the limit of the function f of x as x approaches 0 is equal to 2. So when finding a limit, I'll say it again because it's very important. So when finding a limit at c, f of c is not important. Alright, so this right here, f of c, is not important. It doesn't matter what's happening at that value. It doesn't matter what's happening at x equals 0. It's actually an error, but it doesn't mean the limit doesn't exist. Okay, it's as it approaches it. It's how f of x approaches c from the left and from the right side. So just make sure when we were looking at these limits, we're looking at as x approaches this value of c from the left and the right, what is y getting closer and closer to? We don't care, and that's why the question mark is here, we don't care what happens at 0. We care what happens as it approaches 0. Alright, the next way we can do this is finding limits graphically. So we can graph the limits and see what the limit is as x approaches a certain value. So on the graphing calculator again, I've once again graphed the function x squared minus 7x plus 10 divided by x minus 2. When you plug this in your calculator, make sure you have parentheses in the numerator and parentheses in the denominator. You will get what appears to be just a line, and somewhat true here, but at x equals 2, you see that we have an error right here. So there's something going on. This is a rational function. We have discussed rational functions before, and sometimes there are points of discontinuity, and that's what actually occurs here. So the limit as x approaches 2. So we're still going to do this graphically, but we're also going to look at the table just as well. And so what happens? So you can take a look at your table. As x approaches 2 from the left side, you can see right here, that's from the left side. And then as it approaches 2 from the right side, what is x equals 2? As x gets closer and closer to 2 from the left and the right, what is the y value getting closer and closer to? And so it appears that it's getting closer and closer to negative 3. And so you got negative 2.979899, and then negative 3.030201. So it looks like it's approaching negative 3. Same function, but what happens as x approaches 0? So I've changed my table set to make sure that I start at x equals 0, and then I balance it out just by moving the cursor up or down. And so you can see on this one, now this one doesn't have an error at x equals 0, but once again, we don't care what happens at 0. We care about what happens as it approaches this value. Alright, so as it gets closer and closer to x equals 0, what is the y value getting closer and closer to? What does it appear to be happening? It looks like it's approaching -5. Same thing on part C. So if I just cover this up because I don't want you to necessarily focus on that, but as it approaches it from the left side, you got your -7.030201, and then as it approaches it from the right side, you got -6.9798 and 99. So it looks to be approaching the y value of -7. So once again, when you do your table set, make sure you start with what the limit is you're looking for. So as x approaches -2, make sure you do that as your table set, and then you can do your change as 0.01. So there are some limits graphically. Yes, we are still looking at the table to identify those as well. Here's another one, but if you look, the limit we are now looking as x approaches infinity. So I went ahead and graphed this. You can kind of see the screenshots here. So 1 divided by parentheses x squared plus 1. And then you can see the graph here, at least part of it, in the window. But look at my table set. So my table start is at x equals 0. Okay, and that's not because I'm looking for as x approaches 0, but it's actually going to infinity. But what I changed my table to is to go up by hundreds, because if we're going to infinity, I wanted to go up a lot quicker than just ones. And so you can see my table, at 0 it's 1, and then at 100 you see that 1e to the -4th. Remember, that's times 10 to the -4th, times 10 to the -5th, times 10 to the -5th, -6, -6, -6. So what's happening to that number as x gets larger and larger and larger and larger? It is getting closer and closer and closer to the x-axis, which is when y is equal to 0. Think about this. If you have 1 divided by, let's just say 100 squared plus 1, all right? What is happening to this number? So it's 1 divided by, you have 10,001. So what happens if that number gets even larger? What if it's 1,000 squared plus 1? This number on bottom just keeps getting bigger and bigger. So if you take 1 divided by a really large number, it's just getting closer and closer to that 0 value. So the limit as x approaches infinity of 1 divided by x squared plus 1 is equal to 0. Alright, let's look at another one graphically. We're going to look at a piecewise function here. So we're not going to use the graphing calculator. We're just going to graph this on paper and then kind of answer the 3 questions that I have on limits here. So find the limits graphically. Let's go ahead and graph this piecewise function. So -2x minus 3, we're only graphing values that are less than 0. So if you want, you can do a t-chart and only choose values that are less than 0, but you can also choose values that equal 0, because that's going to be an open circle. So we want to make sure we get that starting value. So if x is 0, we get -3. So when x is 0, it's at -3. When x is -1, it is at -1. And when x is -2, it's at 1. And -3 would be at 3. And you can see that the slope on this one is -2, so it is going down. So if you want to get a couple more points in there, you can. So this will represent this part of the graph. Okay, and then on this next part, it's x squared minus 3, and we only want values that are greater than 0, including 0, even though it's not equal to. We still want to include it, and it'll just be an open circle. So at 0, you're at -3. At 1, it would be -2. 2 squared would be 4 minus 3 is 1, and then 3 squared would be 9 minus 3 is 6. So if we plot these points once again at 0, -3, it's still an open circle, so it didn't get filled in. 1, -2, 2, 1, and 3, 6. 2, 3, 4, 5, 6. And this is a quadratic, so make sure you get that nice curve there. And so now let's go ahead and answer the questions from below in terms of what the limit of each of these is. So the limit of f of x as x approaches 0. Okay? So from the left side, right here is at x equals 0. So as you get closer and closer to x equals 0 from the left and closer to x equals 0 from the right, what is your y value getting closer and closer to? It's getting closer and closer to -3. So as you look at this, you got to go from the left and from the right. So the limit as x approaches 0 would be equal to -3. Let's take a look at as it approaches -2. So -2 is right here. So as x on the graph gets closer and closer to -2 from the left and -2 from the right, what is it going to get closer and closer to in terms of your y value? 1. So the limit of f of x as x approaches -2 would be 1, and then the last one as x approaches 3. So x is 3 right here. So from the left as it approaches this value, and from the right as it approaches x equals 3, what is it getting closer and closer to? And that appears to be 6. So when you're graphing the piecewise function and then you're looking at it to find the limit, make sure you look at it from the left and the right as x approaches that number. What is the y value getting closer and closer to? So in this next part, we're going to talk about limits that fail to exist. So if you take a look at the first one, the limit as x approaches 2 of 3x squared plus 2 divided by x squared minus 4. So I've graphed it for you so you can kind of see what we're looking at here. We changed our table setup to a table start of x equals 2 because once again that's what we're looking at as x approaches 2. So the table starts at 2, and then we're going to change it, the table changed to 0.01. So when we put 2 kind of in the middle so we can see the symmetry here, there's an error, which is perfectly fine. That's not the issue. As you look at this, look at your values to the left. So the values to the left are negative numbers. Okay? So from the left, it's approaching these negative values. From the right, it's approaching positive numbers. Okay, are we missing something? Well, I did it again, but I made my increments even smaller. I did my table change to 0.001. Now, we still have negatives, but the negatives just seem to be getting smaller and smaller and smaller, and then the positives are getting larger and larger and larger. Well, if you look at your graph, you might recognize why that's happening. At x equals 2, we have a vertical asymptote. So from the left side, they're getting really small, and from the right side, they're getting really large. So based on a limit, does the limit exist if you are approaching two different values? Or in this case, you're not just approaching two different values, your values keep getting smaller and smaller and smaller, or larger and larger and larger. So does the limit exist?
Contestants, find the limit of this equation.
Calling somebody else fat won't make you any skinnier. Calling someone stupid doesn't make you any smarter. And ruining Regina George's life definitely didn't make me any happier. All you can do in life is try to solve the problem in front of you.
The limit is -1.
Oh crap, I lost.
That answer is incorrect. And we are in a sudden death. If Miss Aaron can answer this problem correctly, we have a winner.
Limits. Why couldn't I remember anything about limits? Limits. That was the week Aaron got his haircut. Oh god, he looks so cute. Okay, focus, Katie. What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist. The limit does not exist!
Our new state champions, the North Shore Mathletes.
So from that movie, we know that the limit does not exist because it increases, the function increases without bound as x approaches 2. So once again, it does not exist because the function increases without bound as x approaches 2. So it doesn't approach a specific value. Let's take a look at B. Let's take a look at another one of these as to why a limit might fail. So this is a piecewise function. So go ahead and graph the piecewise function. I'm going to pause it. You can graph it, and then we'll take a look at the limit as x approaches 2. So as we take a look at the graph, it is discontinuous, there is a break, but it doesn't mean the limit doesn't exist. It depends on what you're trying to look at. So in this case, as x approaches 2. So as x approaches 2 from the left side, right here being 2, as it approaches from the left side, the y value is getting closer and closer to -1. As it approaches 2 from the right side, the y value is getting closer and closer to 4. So in this case, the limit does not exist because you are approaching two different values. You're approaching -1 from the left, and you're approaching 4 from the right. So the limit does not exist in this case as well. So there's the does not exist, but also explaining why it doesn't exist. It approaches a different value from the right and left side of x equals 2. So limits do not exist if f of x approaches a different value from either side, so that was the second example that we just did, or if it approaches infinity, which means it increases without bound. So it just continues to get larger or smaller as x approaches that number. So there's two reasons why a limit could possibly not exist. Alright, and the last thing we're going to look at is algebraically, and we'll continue this as we go through the rest of this unit of limits. But for now, if a function is continuous, then direct substitution can be used. So what that means is, if we have a limit of f of x as x approaches c, if this is continuous, then we should just be able to plug in c and we will get the limit. Okay, so when we're looking at the graphing calculator, that's when we didn't have those errors, and you realize that the limits were exactly the same as if whatever that c value was. But this only works if the function is continuous. So for right now, that's all we're going to look at with this, is that these are continuous functions. So the limit as x approaches 5 of 3x squared minus 7x plus 2. This is a continuous function. It's a polynomial function, so we should be able to say 3 times 5 squared minus 7 times 5 plus 2 is equal to 42. So the limit as x approaches 5 of the polynomial function 3x squared minus 7x plus 2 is equal 42. Okay. On B, x approaches -2 for the function the square root of x squared plus 5, so we're looking for the limit. So a square root is continuous. There might be some restrictions in the domain, but in this case, because it's the square root of x squared underneath, we should be good. So we will do direct substitution. We'll plug in -2. And what does that give us? That gives us the square root of 4 plus 5, which is the square root of 9. And that is equivalent to 3. So the limit as x approaches -2 of the square root of x squared plus 5 is equal to 3. On example C, once again, we'll use direct substitution. Even though it's rational, your denominator has no restrictions because it is x squared plus 1. So we should be able to just plug in 3 squared plus 1, which is equal to 1/10. So the limit as x approaches 3 of 1 divided by x squared plus 1 is equal to 1/10. And if we did that on the calculator, we might not actually recognize that that value is the fraction 1/10. So we really have to work on algebraically being able to do these, especially when the numbers are not coming out to be nice integers. And then on the last one, we can also use trig functions. So we got the limit as x approaches -2 of cosine of pi over x, or sorry, pi times x divided by 3. So if we use direct substitution, that would be cosine of plugging in -2 for x, so -2 pi over 3. And so what's cosine of -2 pi over 3? That would be in quadrant 3 with a reference angle of pi over 3, so that looks like that would be -1/2. So the limit as x approaches -2 of cosine of pi x divided by 3 is equal to -1/2. So once again, we can find limits algebraically by using direct substitution as long as our functions are continuous. And if they're not continuous, then we'll talk more as to how we're supposed to find those algebraically as well. So there was a lot going on in this video, so please make sure you write those important points. What are those things that you need to know numerically, graphically, and algebraically in terms of being able to find limits. When do limits exist? When do they not exist? So once again, just kind of pull all those things together from this video and summarize them on the last slide.